Welcome to CAETS 2021. I am delighted to welcome Roberto Brandt from Academia Nacional de Ingeniería Argentina, who will moderate Technical Session 3, Renewables.
Welcome to Technical Session 3 on Renewable Energies. My name is Roberto Brandt, and I am a member of the Energy Institute of the National Academy of Engineering of Argentina. In the context of the decarbonization agenda, renewable energies undoubtedly play a pivotal role. However, as underlined by several speakers in our opening plenary, the policies and plans for an accelerated contribution of renewables to significant greenhouse gas emission reductions require structural changes in the existing economic systems and many value chains. The latter creates several opportunities and challenges. Allow me to highlight some of them. On the opportunity side, the outstanding technological progress and cost reductions experienced during recent decades, notably in wind and solar, have created unprecedented momentum for investment growth. In addition, the International Climate Change Mitigation Agenda, as well as the 2050 net zero emission plans and commitments put forward by a large number of countries and thousands of corporations, has enhanced public and private efforts in the fields of research, development, demonstration, and deployment. On the challenge side, it should be noted that, as Bill Gates usually stresses, technology breakthroughs and scaling could take more time than expected. With regard to policies, there is a risk that unidimensional approaches that don't reflect the diversity of regional or national energy sourcing and transition options, or the prioritization of mandatory public regulations over market mechanisms that could help mobilize private investment in sustainable energy in the long term, could increase the cost of energy in the short and medium term. In this line, many policymakers support a green premium in the form of an extra cost that should be paid to ensure the convergence to carbon neutral scenarios. The outcome will ultimately depend on societal decisions expressed through votes and energy consumption. This session aims at providing an up-to-date view of the current and future developments of the main renewable energy technologies, while also covering the supply requirements and prospects of certain minerals that will play a key role to support an accelerated transition towards cleaner energy systems. For this purpose, we will hear from 6 distinguished speakers. Their bios are available on the CAETS 2021 website, so I will introduce them only briefly. Our first speaker will be Ulrich Wagner, an energy economics professor at the Technical University of Munich and a member of ACATech, the National Academy of Science and Engineering of Germany. He will describe the contribution of complex energy systems modeling to technology and investment decision-making and to CO2 emissions management. He will be followed by Atsuo Yamada, professor of the Department of Chemical Systems Engineering at the University of Tokyo, Japan, who will cover energy conversion and storage batteries. The third speaker will be Masakatsu Sugiyama, professor of the Research Center for Advanced Science and Technology of the University of Tokyo, who will focus on hydrogen. The next presenter will be Eloy Álvarez Pellegri, Secretary General of RAE, the Royal Academy of Engineering of Spain, who will share the European and Spanish development plans for hydrogen and biofuels. The fifth speaker will be our Argentine colleague, Martín Pérez de Solay, CEO of the Australian mining conglomerate Orocobre, recently merged with Galaxy Resources. He will discuss the supply status and prospects of raw materials that are key for the development of renewables. The last speaker will be Oscar Ferreño, Institutional Relations and Regulatory Affairs Director of Ventus and member of ANIO, the National Academy of Engineering of Uruguay, who will address variability management in wind and solar power generation. I would like to encourage the audience to submit written questions to the panel through the Zoom chat during this meeting, and we will address them after the presentations. Please note that at the end of the session, Hamed Beheshti from the German company Borean Light and Sebastián García Marra from the Argentine firm Les Industries will share brief presentations on their businesses that have been selected by the World Energy Council as finalists for the Startup Energy Transition Awards. Ladies and gentlemen, I hope you will enjoy this high-quality immersion in the opportunities and challenges of renewable energies.
Ladies and gentlemen, welcome to my keynote on new energy system modeling, which should bring together technology, market, and society. So my first question is, why energy system modeling? Then I'll have a short remark on the methods of energy system modeling. And then the most important point, of course, the challenges and possible conclusions. So first point, why energy system modeling? So if we consider the increasing challenges for energy systems with regard to climate and environmental protection, energy system modeling becomes more and more important for many purposes. So this starts, for instance, when looking at detailed energy management concepts in a company, or energy concepts in community, in local cities, or energy scenarios at a national or even at a global area. So energy system modeling helps understanding complex systems, and it can show, for instance, paths of no regret or no-goes, saves time and avoids costly try and error experiments. So at the very beginning of energy system modeling, we have to have a good picture of the state of the art of the energy system. And in this picture, I show you one example which addresses Germany's energy consumption and emissions by application sector for the year 2017. In the upper line, we see the final energy consumption, and the lower part, the CO2 emission. And just to pick out two examples, if we look at the residential area, we have, of course, lots of energy for space heating. We have energy necessary for drinking warm water preparation, for cooking, for mechanical energy, and so on. And to get this information is already quite complicated, because this is not a result of national statistics, which only consider the consumption of energy carriers in different sectors. But at the beginning of the energy chain, of the process chain, we have the user which needs energy for something. And we do not have quite a solid picture of the energy needed or the purposes for the energy needed. So this is the first step at the beginning of the energy chain, understanding the principle of the energy system. Second example is the industry, where the picture is even more heterogeneous. Depends very much on the national situation, what kind of industry, is typical for the country, so heavy industry or services and so on. And in the case of Germany, we see, for instance, lots of energy used for process heat from low temperature up to higher temperature, more than 500 degrees centigrade. And of course, so not only the terawatt hours of energy count, but the quality. What quality does this energy have? So in this special case, the heat, low temperature or high temperature. This is quite important when talking about substitution from fossil energy carriers by renewable energy, by hydrogen or whatever. So this sounds perhaps trivial at the first sight, but it is not. It is quite hard work to find out this principle. So the second step then is translating the final energy consumption into CO2 emissions, because CO2 emissions are normally the aspects where the political goals addresses to, not so much energy, but CO2 emissions is the most important aspect. And this, again, a picture for Germany, which shows us the emission of CO2 during 1 year, in this case, the year 2016, and now split up between the different forms of application. So lighting, ICT, air conditioning, mechanical energy, process cooling, process heat, space heating, hot water, and this broken up to the 4 consumption sectors: transport, private household, industry, and commerce and services. And this picture, I think, is very enlightening because it shows us at the first sight where the most important bars, the pillars are here in these pictures. So we see that mechanical energy in transport is the dominating sector. We have space heating in private households. We have process heat in industry. We would have expected that, of course. And mechanical energy for industrial purposes. So these are the most important consumers of final energy. And if we look at the rest, we see lots of facts and figures which do not play such a big role. And well, what we learned from this picture is where we should address or focus first. So these are the big hubs. And by the way, divided into the direct CO2 emissions, which is the lower part of the bars, and the indirect CO2 emissions, which comes from upstream, so from power plants, from refineries, especially for district heating plants and so on. And this is also part, of course, of the CO2 emissions related to a special application in a special sector. So having said this, a few comments to methods of energy system modeling. We have many variants. So bottom-up principles or top-down principles depends on the question we have to the energy modeling. So the corresponding resolution in time and space plays a big role. So the granularity, whether we model the energy system in periods of 1 year, or if we look at the electricity system, it's nowadays more important to have very short time periods, even going down to 1 second of time resolution, because the CO2 emission depends very much not only on the energy carrier, but in case of electricity, also on the time when you use the electricity, whether there is a lot of PV in the system, or is it lignite power plants which dominate the generation of electricity. So we have deterministic and heuristic concepts, linear programming, Monte Carlo, and if we look at market models, agent modeling plays a more and more important role. And one of the main goals of the calculation of energy scenario is well, to show possible path in order to fulfill governmental goals for CO2 reduction and show sensitivity of different parameters. Does it play a role, or which role does it play to increase the efficiency of building, or to switch from combustion engine to electric mobility, for instance? So the most challenging point, of course, is after having understood the status quo of the energy system, to have scenarios for the future. And relating to this, also one example only, also addressing the German situation. Sorry for lots of information inside, but I will not go into detail. Just show you what is necessary for understanding the scenario technology. This picture shows us the development of the electricity consumption and generation in Germany for the years 2020, 30, 40, and 50. In the upper part, we see the generation, where the electricity comes from. So today, 361 terawatt hours still come from fossils and 258 from renewables. And renewables will steadily increase, fossil will go down. This is the one side. But as I mentioned in the beginning, of course, the trigger for this generation is the consumption. So this is the consumption of electricity, which in the case of Germany will increase due to more heat pumps, due to more electric vehicles, for instance. And of course, we can go into details of any parts of these bars. Who is the consumer? How will the consumption of energy change over time in traffic, in households, and so on? So this is still having a look at the energy system, and as the title of my keynote also addresses, it's much more important and decisive in the future to couple energy system modeling with market principles, with societal and political aspects. And of course, we are engineers. We can understand the technical system quite good and simulate and model it. Meanwhile, we are also able to simulate the market, different market mechanisms, for instance. It's more complicated to simulate or make a prognosis on the user behavior. We are still learning by statistical and societal measures to better understand the user behavior. And the most difficult thing is simulating political decisions. We are still not able to simulate this, and I'm afraid that we never will. So we have to make assumptions on what could happen on a political scale. Yes, to draw some conclusions from this. At the start, we have the need of realistic technical models of today's energy system. So this is indispensable, and the quality of our scenarios and of our prognosis depends completely on the realism of our models. And then we have to be very creative and find new options of technologies, how to integrate renewables, find out new business cases, new market mechanisms, blockchain, for instance, and these new aspects have to be implemented in our modeling. So then come the societal and political aspects, as I mentioned, which are increasingly important, and this makes it necessary to cooperate much more than in the past with our colleagues from the corresponding faculties from societal and political side. Very, very creative, very interesting experience, by the way, bringing those faculties together, because the mechanisms and methods we work with are quite different, but it's necessary to find creative ways for this cooperation. In the end, modeling helps designing complex energy system and saves a lot of time, can save a lot of money if we look at some political decisions, also in Germany, where For instance, the subsidies for the renewable were declined without having a clear picture of the possible consequences, and we could have predicted many things without trying them out in a try and error principle. Yes, the final conclusion is that we scientists, we analyze possible scenarios. We have to be very creative in this, very cooperative. We can deliver sensitivity analysis for different factors. So what is the consequence of phasing out of nuclear, for instance? CO2 emissions will rise. Will we be able to compensate this by introducing more renewable energies? Is this realistic? How much does it cost? So these are the facts and figures we can deliver, and hopefully as a basis for sensible political decisions. Thank you very much.
All right, I've talked on the impact of energy storage to the future society. My name is Atsuo Yamada from the University of Tokyo. All right, let me briefly introduce myself. I started my career at the Sony Research Center for 13 years and moved to the Tokyo Tech, and now in the University of Tokyo. During that period, I was staying in the University of Texas with John Goodenough, who who won the Nobel Prize 2 years ago. So I have about 25 years career for the energy storage and battery system and battery materials. So storage is a very important term for the human beings. So if we look at the food in the hunting era, we should eat it just after the hunting, but we invented the agriculture and low temperature storage, which makes our life very rich. And now we enjoy the very nice eating cultures. And information technology is also important. We have invented the paper to make the storage for the information, and now moved to the magnetic storage and electricity storage. Now we're using the cloud storage, which also enrich our daily life. And the wealth storage is also important. We invented the banking system and the economic system, which can allow us to store the wealth. And that was very important role, that has important role in the present societies as well. But for the energy, maybe we can call we are still in the hunting era, because we are forced to use the energy just after it was generated, or in the many cases. If we change the culture to the freely store the energy every day and whenever we like, that will largely change our human being society. So in that term, the battery should play a very important role. So we can categorize the energy storage system and the generating system like this. In the closed system, we have the primary battery. We cannot make the rechargeable reaction. And the focus on today is the secondary battery. We can make a rechargeable reaction very easily. We have a fuel cell, but we should not call it the battery. I think it's an electric generator by the fuel supply and the gas exhaust. So we focus on the secondary battery today's talk. So for the future society, for the carbon neutral in the near future, we need to shift to the renewable energy system sites such as solar or wind. But unfortunately, we cannot control it. So to make and control it, we store the electricity for the difference of the demand and requirement to the battery, and the difference of the energy, or it should sometimes move to the hydrogen to make the chemical reaction. For the battery system, we are making use of the electric vehicle or the local storage system, such as the individual house. So for the individual house, we can make a self-management and energy by putting the solar cell on the roof and put an electric vehicle to make use of the vehicle to home system and make a special battery to make the self-management of the total home system. So for the electric vehicle societies, we are the government of the many countries have setting the restriction in the very short term to prohibit the use of the combustion engine, such as 2025 and 2030. So also for the car company like the Daimler and General Motors, who invented the combustion engine for a long time ago, now begin to stop to develop the combustion engine. So movement for the electricity transportation is now is making a very huge wave in all over the world. So for the electric vehicle market, in the next 10 years, it was said that 30 times the battery will be produced. When we move to the next stage for the infrastructure for the electricity, the storage, the market should be much, much larger. So the battery market is growing very, very rapidly. Maybe we can call it exponential like. So for that kind of direction towards sustainability, material sustainability, we are looking at the elemental strategy like this. So now we are using the rare elements such as lithium, cobalt, and nickel, and flammable organics that can cause something catch fire. So we should shift to more abundant elements such as sodium and iron, manganese, titanium, and instead of the organics, we should use maybe for example, water, H2O. So such kind of direction, research direction is very important. And actually I am involved in this kind of project in Japan. So let's briefly look back at the history of the rechargeable battery. Maybe we can call it that we have the 150 years of the history. But for the long time, only the two kinds of rechargeable battery exist at room temperature operation, such as lead acid battery and nickel cadmium batteries. About 30 years ago, the nickel metal hydride battery and lithium ion battery has invented almost at the same times in Japan, and the Japanese company has beginning to mass production. Now the level of the lithium ion battery is reaching to 200 watt per kilogram, which may call it the benchmarking and the energy density limit. If we want more energy density larger than 200, maybe lithium metal should be used instead of the graphite, which we're now using, or maybe we shift to another chemistry other than the lithium ion system. For the target of the source in the cycle, the calendar life should be set much better. Now it's in level of the 500 cycles, and the electric vehicle, maybe we are reaching the 2000 cycle, but for the stationary use for the infrastructure, we should realize the more than 10,000 times. And that meaning that the lifetime should be 5 years for portable electronics and 10 years for the electric vehicles, and maybe the more than 30 years for stationary use for infrastructures. The cost is now reaching to the $500 per kilowatt per gram, but for the infrastructure, for the huge amount of the application, we need to reduce it to the $100 per kilowatt. In terms of this, and the elemental strategy is also important. So if you look at the power, not the energy density, so this is the level of combustion engine. So then the battery technology have almost exceeding the combustion engine level. And the motor technology have also realized a much larger power than the combustion engine. That is why if you experience an EV, the acceleration power is much better than the combustion engine. So this is the reason that the electric vehicle can make the sophisticated system for the acceleration and the total system for the controlling, including the self-driving. So why we call the lithium ion battery rather than the lithium battery. So the term ion has huge meaning in this. So if we use the lithium metal, like this is include Japanese, but then if you use the lithium metal is most efficient because it's high energy density, but the inhomogeneous reaction always causing such short circuits inside the battery like this. So that this is a very dangerous situation. So this is why for the long time, the lithium metal battery cannot be used and commercialized. So invention of the integration system like this to solve this problem. And this is the technology the Nobel Prize was awarded for 2 years ago. So instead of the use of lithium metal, we used a framework structure for material like this, and graphite for the anodes, for the oxide, and phosphate for cathode materials. So which makes it very reversible for the reaction. So now the cathode is using such like this, including cobalt and nickel, and now shifts to the lithium iron phosphate, including the abundant element and the iron. So if we increase in the amount of nickel, the energy density is increasing. And if you look at cobalt, that is a little bit stabilized for the system, but cobalt is a rare element. We need to remove it. And lithium iron phosphate is advantageous for the cost and stability, and very important for the safety issues because oxygen is not evolved from this structure by the covalent bonding between the phosphorus and oxygen in the framework structures. So for the integration chemistry, 2 years ago, the Nobel Prize was awarded to these three famous professors. So I'm very happy that I worked with John Goodman, one of the Nobel Prize winner in 2 years ago in 1997. That's maybe more than 25 years ago, but it was a very good memory for me. So another important issue we should consider about for the battery system is the safety. So the high energy density means that if that is released in a very short time, it's a very hard, it causes very serious reaction for the combustion because the present battery, including the flammable organic electrolyte inside the battery. So we can see this is very often in the newspaper for explosion or not PC or EV, and we should avoid this kind of thing. And there's very serious problem for the safety issues. So now in the battery development is meeting the dilemma between the safety and energy density and size of the battery. If we increasing the energy density and size of the battery for the larger scale, the safety issue should be much more serious. So there is a trade-off between this kind of size and the energy density between safety guarantees. So we need to make a compromise development for the battery system. So we should keep this in mind. So bearing these kind of background in mind, so we should think about where we are and where should we go for the next stage for the human beings. So we should carefully discuss on this point, what is really the innovative and next generation and what is really necessary and for the higher point of view, and the frontier research versus terminated research, we should distinguish them. So let us overview the present battery technologies. Of course, the lithium-ion battery is the prestigious one, the most advanced one, and we can set it at benchmarking. So if we want a high power and very long time, we can go to the capacitor system, but the energy density is very low. So for the higher energy density, we should move to another chemistry, including the use of the metal and another chemistry and ion transport, using sulfur decomposition, reversible decomposition, or use a magnesium 2+ aluminum 3+ battery. But they're still in the very primitive stage. I did not see any promising system and device performance so far. So the most promising is the direction, of course, of the derivative of lithium-ion batteries using the exchanging the electrolyte and the replacement of lithium to sodium, much more abundant sodium, and the placement of electrolytes is a much more abundant aqueous system and water system. These are the most promising and short-term research we should explore in the short term. And another direction is made in solidification, using the solid electrolytes, that's a polymer and then inorganics. So this is the stacking level energy density can be higher, but this is still in the very early stage of development, and I didn't see any promising result in device and system level yet. So in the Japanese strategy is the elemental strategy that I am actually involved in this project, and we're looking at the short term. And for the long-term research, there is another project in Japanese Rising 3 and Outer Spring, and then spending much more money. And the solidification and the target is the usual, mainly for the electric vehicle. And the Japanese market has put huge money for this direction as well. Okay, but for the short term, maybe, as I said, the derivatives such as the lithium-ion system derivative should be then promising for at least for the next couple of decades, I think. So it's a good idea to leverage the Tesla's heuristic strategy. They are making a strategy depending on the application, changing the cathode material, lithium-ion phosphate, and the nickel and manganese layered, and the nickel-rich layered materials. So for the stationary use and low-cost electric vehicles, they are trying to use in lithium iron phosphate. The market of lithium iron phosphate should be expanding for the next decades for sure. And for the middle range EV, or for the power wall for the house, they are using the nickel less materials. But for the large scale, large vehicles, the weight is really necessary, important that the nickel-rich direction is exploring, but we should think about the safety issue for this case. For the coming market, lithium ion phosphate should be dominating, I think, because of the huge market for the small vehicles, for low-cost vehicles here. So we should carefully looking at the direction for this important materials for the coming decades. Then the cell size is larger and the system is simplified like this. The hierarchy of the system is reducing. So this kind of realistic direction is going on in the world, and we should carefully look at this direction for the next coming decades. So let's end up my talk by we should look at this derivative for the coming year. For the long time, we should look at much more exotic system. All right, thank you very much for your attention.
Good morning, everyone. I'm Masakazu Sugiyama, belonging to the University of Tokyo and the Engineering Academy of Japan. Today, my talk is on the role of the hydrogen for massive dissemination of the renewable energy sources, and especially I'll focus on the Japanese situation targeted at the 2050 carbon neutrality goal. And as you know, the intermittency of the renewable energy source power generation is the severe problem. So as is written here, the demand of the electricity changes with time, and we need to have the power generation so that the demand and generation matches every timing. But once the massive installation of the renewable source, such as the photovoltaic, starts, then we definitely need another adjustable power generation so that the sum of the renewable and adjustable power generation matches the demand of the electricity. But that actually imposes us the quite a severe control, such as the reduction of the bottom line of the adjustable power generation, and also the quick rise of the power generation with time. So in the situation of Japan, now the penetration of the renewable is quite good, so that the total amount of the cumulative installation of all the renewables is almost approaching the half of the maximum power generation in Japan. So that actually makes quite a difficulty of the grid management, as I have told you. And one example is here. In the southern part of the Japan, the Kyushu Island, the power generation is here, combining the photovoltaic and the fossil thermal generation and the nuclear there. And in that particular timing of the around noon, then the power demand in that particular island is as small as this one. And they try to transmit the electricity to the neighboring zones, grids, and also they try to use the pumped hydro as a large-scale electricity storage. But still, there is a huge mismatch as it's written here. So they now have to curtail the output of the solar power generation quite frequently, as it's written here. Facing that kind of the situation, we are now thinking about, again, how to allow us the much further installation of the solar and wind power generation, which are renewables. And since these modern renewable power sources are always giving us the electricity, not the directly fuel, so we need to increase the electrification and increase the demand of the electricity as a substitute of the fossil fuel usage with electricity. And electrical vehicle is one of that method. And also in the region which is cooled, then the heat pump is also a very nice method to substitute the fossil fuel usage with the electricity. And these two methods increases the demand of the electricity and reduce the demand for the fossil fuel. But that not only increase the installation of the renewables, but also the necessity of the adjustable power sources. And that has been maintained by the firing of the fossil fuel. So in order to make it possible, the deep penetration of the renewables and deep decarbonization, we need to substitute that fossil fuel with the fuel which never emits CO2 in its entire lifetime from the production to the usage. And at this particular moment, at this existing moment, the only technology that allows that purpose is hydrogen. So the hydrogen can be used for the mobility's powering and also the providing the high temperature heat for industries. But more importantly, hydrogen can be used as the fuel for the electricity generation. And of course, we have another option of the distributed power system with the massive amount of the power storage like batteries. This is, of course, a very important alternative technology. But especially in the region like Tokyo, with a very high population density, then we need to still maintain this kind of the centralized energy distribution system in terms of the both electricity and the fuel. So in that situation, the hydrogen is a vital method for allowing the deep penetration of the renewables. And this is the latest national goal for the decarbonization of our energy system towards the 2050. At this year, the Japanese government recently committed the goal of the carbon neutrality achievement. And in that particular scenario, the one important point is the increase of the electrification as is written here. And it is written that the 30 to 50% increase of the electricity demand will be targeted. And that actually is accompanied by the fraction of the renewable penetration more than 50%. And another point for the sector which is not yet electrified or hard to be electrified would be the use of the CO2-free hydrogen. And the amount of the use of the hydrogen targeted at this 2050 is 20 million tons per year. This is a large amount. And talking about that, a penetration of the renewable electricity, actually, in Japan is suffering from the shortage of the land area. So, according to this estimation of the possibility of the renewable installation in Japan, even we follow the maximum expectation in 2050, the installation of the modern renewables like photovoltaic and wind are not satisfactory. And in that old estimation, the possibility of the offshore wind power generation has been dismissed, so we can still append the 30 to 40 gigawatt wind power generation, to this wind sector. But still, the total expected power generation is something like 700 terawatt hour. And that amount is just hitting the lower limit of that expected power generation by renewables, which allows for the carbon neutrality target at 2050. So the message here is that, at least for the case of Japan, the penetration of the renewable electricity sources are quite difficult, so that we can cover the entire amount of the renewable electricity expected, which realizes the carbon neutrality target. And this is one typical case. So in order for the residential installation of the photovoltaic to achieve this number, then we need to install the photovoltaic, not only the normal rooftop, but the rooftop facing to the north, and also almost all the walls and windows. This is a very extreme installation and not easy to achieve. So that's why the people in Japan are expecting another method of decarbonizing our energy system with hydrogen. And this is the cartoon presented by the Japanese government, how we can facilitate that installation of the hydrogen. So historically, the Japanese government has been pushing the installation of the hydrogen utilization infrastructure. And recently, they also focus on the domestic generation of the renewable hydrogen, as is presented by this very pioneering 10 megawatt alkaline electrolyzer installed in the Fukushima region. And this year, there will be a very important demonstration of our import of the hydrogen from the overseas countries. In this particular case, the hydrogen will be coming from the Victoria, Australia, to Japan by the ship, which can carry liquefied hydrogen. And that kind of policy has been summarized in the Japanese basic hydrogen strategy. And that strategy was presented at 2017, almost 4 years ago. And after that, there is now the very recent update of the policy regarding the use of the hydrogen. So the Japanese government aims at much more aggressive installation or penetration of the fuel cell-driven mobilities, not only in the personal mobility, but rather for the large mobilities like trucks and the trains. And also, the aggressive cost reduction is regarded to be a necessity. And as a result, as I have already mentioned, the amount of the hydrogen targeted at the 2050 is 20 million ton. And the breakdown of that 20 million ton hydrogen per year usage is not explicitly written in the Japanese policy paper. But if I interpret that personally, that 20 million ton per year is almost 1/3 for the power generation, electricity generation. And 1/3 is the mobilities, especially the long-haul trucks and trains. And the last 1/3 is the material fabrication, such as the steel making. So this amount of the 20 million ton per year is so large again. So let me make some light exercise of our brain. How much electricity do we need to produce that 20 million ton per year hydrogen solely by water electrolysis? And it is easy for us to answer to this question. The 1,000 terawatt hour per year electricity is necessary for this particular purpose. And this amount of the electricity is exactly the same one as the existing electricity generation in Japan. That means in order to obtain this amount of the hydrogen by electrolysis, we need to double the power generation domestically in Japan. That is actually not easy. If we rely on the photovoltaic power generation as an example, here is the case. This is the flat land area, very limited in Japan, and that necessary area for the generation of this particular amount of the electricity will almost occupy the major flat land area in Japan. So I'm now living in Tokyo, but I will be kicked out if the Japanese government takes this strategy of making the additional 1,000 terawatt hour electricity by photovoltaic to generate this amount of the hydrogen. But if we go to another country, like in Australia, this area which is necessary for the generation of this amount of the hydrogen will still be possible. So we need to think about the story like our existing case of the importing of fuel from other countries. In the future, we probably have to at least import a fraction of our necessary hydrogen from abroad. That's why Japanese government has been invested not only for the infrastructure for the utilization of the hydrogen, but also for the technology which allows for the massive transportation and in some cases storage of the hydrogen. And those are the use of the ammonia as fuel or the direct liquefaction of the hydrogen. But also we have a technology of the using some molecule to stabilize the hydrogen, which is the conversion between the taurine and methylcyclohexane, MCH. But one more important point is that those hydrogen, in the ultimate sense, need to be generated from the renewable source so that we can facilitate the deep decarbonization. So here is one ongoing approach of the use of the ammonia as a fuel to reduce the carbon footprint out of the coal firing power generation. And the only important point here is that in order to make this a 20% mixed combustion of the ammonia with the coal existing in the existing power plant, we will exceed the existing worldwide trading of the ammonia so that we can secure the new hydrogen source. And this is the last slide. That new hydrogen source needs to be CO2 free. And the point is that how much capacity can we generate that CO2 free hydrogen out of the renewable sources? Probably this will be easy because we have a very abundant land area in the entire world. But people also think about the use of the low-cost CO2 free hydrogen. This is what is called the blue hydrogen. But the capacity of that generation of the blue hydrogen to cover the entire hydrogen demand in the world, this will be the question. So in order to allow for the deep decarbonization of our energy system in the entire world, we probably need to cultivate the possibility of the green hydrogen generation in the accelerated manner. So this is the end of my talk. Thank you for your attention.
First, I would like to thank you, the CAETS organization, and in particular the Academia Nacional de Ingeniería de Argentina, the possibility to address this important annual conference of CAETS in the matter of energy. I would like to address the issue of hydrogen and biofuels from the point of view of Europe and Spain. In the first block, I will refer to hydrogen, the second one to biofuels, and then I will finish with some final remarks. Well, the general context, I believe it's important in the sense that since 2015 with the Paris Agreement, and in particular since 2017 with the creation of Hydrogen Council in Davos, then have been a number of studies and publications and the support of some international institutions that provide a framework for the development of the strategy of hydrogen in the European Union. In terms of hydrogen itself, the strategy of the European Union is clearly established in a document of the communication of the Commission of the year 2020, so very recently. The priority is to produce and develop renewable hydrogen. The intention is to develop at the same time a hydrogen ecosystem that is likely to develop in a gradual way. And the European Commission recognized that the clean hydrogen is not competitive and requires huge investments. The European Commission distinguished 3 periods, 2020-2024, from that year to 2030, and 20 years from 2030 to 2050. There are quantitative objectives, at least in the first period, 6,000 megawatts of renewable hydrogen electrolyzers. The idea is to develop installations next to existing demand centers, particularly refineries and steel plants, and develop hydrogen refueling stations. For the second period, hydrogen needs to be an intrinsic part of the integration energy system. The idea is to develop at least 40 gigawatts of renewable energy, producing 10 billion tons of hydrogen, and that because of these economies of scale and increasing quantities produced, the idea is that gradually renewable energy becomes cost competitive. However, dedicated demand side policies will be needed. For the period 2025-2030, it is assumed also that the hydrogen will become abundant and cheap, that will be used also for seasonal storage, and will be needed a European Union-wide logistic infrastructure. The advantage of this hydrogen should be that the existing gas grid could be partially utilized or repurposed. For the last period, the idea is that the renewable hydrogen, should reach maturity, should be deployed at large scale, and should be very useful to reach all hard to decarbonize sectors. As mentioned, the huge investments are necessary. In the document of the European Commission, it is estimated a level of 42 billion euros investment in electrolyzers, besides the investments needed in wind and solar energy, and the infrastructure needed for transport that is estimated for the period in 65 billion of investments. The European Commission relies very much on the European Clean Hydrogen Alliance for the investment, and consider also that the European investment shall also be key as an instrument with the support, for instance, of the European Investment Bank. Therefore, the strategy of the European Union relies on boosting demand, designing and enabling supporting framework, and promoting research and innovation. The Spanish roadmap for renewable energy follows the strategy of the European Union, as is quite obvious. And our plans are established basically in detail in the Plan Nacional de Integrado de Energía y Clima, in the National Plan on Energy and Climate for the period 2021-2030, and also with Energy Transition Law and Climate Change Law that has been recently approved by the Spanish Parliament. As it is clear, the Spanish strategy is in the framework of the European strategy and putting some specific objectives to Spain. In particular, it is expected that 4,000 megawatts, 4 gigawatts of electrolyzers should be developed for in this decade till 2030. That 25% of the total consumption of hydrogen in the industry should be supplied by renewable hydrogen. That also 150 buses of fuel cell electric vehicles should be in place, and roughly between 5,000 and 7,500 vehicles of fuel cell electric vehicles provided of fuel by hydrogen. Development of refueling stations is also contemplated, with some objectives in a range of 100-150, and it is estimated that should be needed for that development 9,000 million of investments of part are expected that could come from the funds of the European Union, from the resilience transformation of the economy. It is important to mention that the competitiveness is recognized not only by the European Union, but also by other elements as the international other institutions and studies. This is a graph that provides a clear picture of the differences in prices between hydrogen produced by natural gas or coal and renewable hydrogen, that is roughly in the half, actually in the half of the estimated cost of renewable hydrogen. And also it is important to mention the sensitivity of renewable hydrogen costs to the price of the electricity, as this graph clearly shows. In the horizontal band, it is the band of the prices for fossil fuels production of hydrogen, and the slopes tries to show the electrolysis costs coming from different capacity factors. This graph is also useful as mentioned the sensitivity of capacity production, of number of hours of production of electrolyzers to the competitiveness of hydrogen. Really, now I would like to pass to the second block of the presentation that refers to biofuels. Biofuels really are understood by the recent renewable energy directives that colloquially it is referred as RED II, because it's a revision of the renewable energy directives of 2009, in which it is stated not only the objective of the gross final energy consumption, but also the objective of the penetration of biofuels in transport, with the number of 14 in the year 2030. The idea is that part of these biofuels should be advanced biofuels, and at least 3.5% in the year 2030, and coming from the level of 2.2% in 2020. I would like to stress that the directive details sustainability criteria for the production of biofuels, not only stressing the penetration of advanced biofuels, but also putting some conditions and limits and criteria for the production of biofuels in the sense that trying not to compete with the production of food by agriculture. In Spain, to a certain extent, it is the same that hydrogen. The strategy, it is clear in the framework of the European Union. The objective of 2020 that was previously, some years ago, the level of 10% is now 8.5%, with a growth from the level of 21 and 22 of arriving to 10%. Again, the advanced biofuels with a limit of 7% to produce biofuels from agricultural products, and considerations, as mentioned, of the indirect land use change. To give an idea of the situation in Spain, this graph shows you two periods, one from 2009 to 2012, and then the level of 2013 to 2018, in which you can see that after a considerable drop in the year 2013, because the objectives were not being complied and the requirements were slightly changed, the level of growth was again regained to trying to obtain the level of 8 to 5% in this year 2020, last year 2020. In Spain, we have a local production or domestic production. We have nearly 20 biodiesel plants with a capacity of roughly 3 million tons per year, and with actually it is at half of level of capacity with 1.4 million tons per year. There are 4 bioethanol plants with a capacity below the 500,000 tons per year, and a production that is more close to the full capacity of the facilities. And I would like to finish mentioning the matter of biogas, because the European Union stressed the production of biogas from different uses and also for transport. It is also stressed in the Spanish roadmap. In fact, in the month of July, this last July, really even I think was in the month of nearly August, the Spanish government published a pathway to biogas in Spain that is, of course, contemplated in this National Integrated Plan for Energy and Climate, and in the government, as I mentioned, has recently published this roadmap for biogas. It is in relation to biogas for transport, no binding objectives, although there is the indicative objective of 1% of biomethane in the year 2030 to be injected into the grid. And the roadmap includes measures and proposals for regulation, objectives, incentives for development of affected zones for energy and promotion. It is important to say that really most of the biogas facilities that are producing biogas are really producing nearly 2.7 terabytes of energy, but most of it is going to generating electricity and a small part for heat. There is only one facility in Spain that injects biomethane to the grid, and as it is well known, really, in order to be used biomethane in transport, the biogas should be depurated and conditioned, and also transferred to biomethane to be compatible with the facilities in the gas vehicles, and also with the grid weather distribution on transport, although biogas is expected to be injected into the distribution grids only in facilities close to the point of production. Well, I would like to finalize with some final remarks, really trying to a certain extent to summarize the points that I have been raising. My first point, my first remark is that there is a favorable context for the development of renewable hydrogen, not only in the international context, as I tried to mention at the very beginning, but also in the European Union and, of course, in Spain. European Union supports really the strategy for renewable hydrogen, and it is aware of the high cost and the huge investments that are necessary for its development. It is also worthwhile mentioning that renewable hydrogen strategy is a long-term strategy, so implies many years of development. The Spanish strategy, to a certain extent and mostly, mirrors the strategy of the European Union, and of course puts objectives consistent with our size of our energy system, of our economy. The European funds for resilience and transformation are expected to be a stimulus and are expected to develop specific projects of electrolysis of hydrogen logistics in Spain. But it is worthwhile recognize that it is unknown how developments shall take place, particularly in such a long period of strategy. And referring finally to biofuels, have quantitative objectives for penetration in transport that are in the level of 14%, 10% in the medium term till 2030. And it is also worthwhile mentioning that has been a reduction on previous objectives, so try to reflect probably that the difficulty of the penetration of biofuels and renewable energy into the transport as a final energy, and also the strict requirements for sustainability that implies the development of biofuels. So this also suggests that accomplishments of the objectives should require continuous efforts. I would like to finalize again to giving thanks to the CAETS, to the organization, and to the Academia Nacional de Ingeniería de Argentina for giving me the opportunity as a member of the Royal Academy of Engineering of Spain to address this distinguished audience. And I would like to finalize saying thank you to all of you for your attention to this presentation. Thank you again.
Energy transition. Energy transition is a process of shifting the world's energy system from one based on fossil fuels to one based on clean energy. Electrification allows for the use of carbon-free electricity in place of fossil fuels, also improving the overall efficiency of the system. Electric vehicles, for instance, are more efficient than internal combustion engines. Fossil fuels are widely used because they deliver large quantities of energy per unit of volume and are easy and relatively cheap to handle and transport. They can also be stored for indefinite periods. However, they are not renewable, and the increased emission of greenhouse gases challenges the achievement of climate change targets. McKinsey & Company's preliminary projections estimate peak demand for fossil fuels by 2027. To stay on track for net zero emissions by 2050, in 2030, annual production of electric vehicles needs to be 10 times higher than it was last year, and the number of roads at charging stations 31 times bigger. The installed base of renewable power generation needs to rise threefold. Global mining firms will have to increase the annual production of critical minerals by 500%. What we need for the energy transition, we need to deal with the difficulty of having many renewable sources, which is intermittency of supply combined with its unpredictability. One of the crucial features of the future energy supply systems will be the integration into a stable power supply that can track the demand curve. Sources that are designed to supply electricity continuously will be harnessed to provide base load, while the maximum demand or peak load occurs only brief around 6 p.m. on winter evenings for about 300 hours a year. The rapid increase in demand can be satisfied by a reliable rapid response energy storage system into more easily transportable hydrogen and oxygen, and either use of fuel cells to recombine them, releasing electrical energy, or burning hydrogen as a fuel. When we look at electric vehicles as a key part of the energy transition, what we have seen is that the battery electric vehicles' popularity is outpacing estimations driven by increased global focus on decarbonization, continued technological improvements in driving down battery costs, and increased government stimulus on the sector. Estimation of 40% electric vehicle penetration in 2030 sees lithium-ion battery demand at 2,600 gigawatt-hour in 2030 versus 150 gigawatt-hour today, while energy storage systems should account for additional 130 gigawatt-hour demand by 2030. Further, the average battery size is expected to increase as hybrids lose market share and higher performance model enter in the mix. UBS's base upside and lower and downside scenarios for 2025 see global electric vehicle penetration at 17%, 28%, and 7% respectively, resulting in a global battery demand between 400 and 1,600 gigawatt-hour, at least 3 times higher than the current demand. How will the transition to electric vehicles occur? Governments globally are largely aligned with promoting electric vehicle mass adoption. To date, more than 20 countries have announced a full phase-out of internal combustion engines car sales over the next 10 to 30 years, including emerging economies. Moreover, more than 120 countries that account for around 85% of global road vehicle fleet have announced economy-wide net zero emission pledges. 10 million electrical cars were on the world's roads in 2020, while sales of electric cars were 5% of total sales around the world. The availability of electric models expanded, and new initiatives for critical battery technology were launched. Despite a turbulent year, major companies around the world are accelerating the transition to electric mobility by shifting fleets to electric vehicles and installing charging stations. Are we entering an era of electric vehicles? China has still more electric vehicles on the road than any other country in the region, but Europeans overtook China as the world's largest buyers of electric vehicles in 2020. The US is the third largest market for electric vehicles, and after recent announcements made by the government regarding climate change, this market is expected to grow significantly. Driven by regulations, national incentives, and new sustainability mandates, 50% of new car sales across the European Union could be electric vehicles by 2030. Individual countries in the region provide cash incentives as well, which range from 2,000 euros in Italy to 9,000 euros in Germany. China's electric vehicle market enjoys several years of near doubling sales thanks to generous subsidies for buyers. But in 2019 and 2020, they were half the level given China's economic recovery and lower incentives. How the electric vehicle demand translates into battery materials. Electric vehicle demand is still uncertain, but most recent sales indicators, particularly in Europe, show a promising future. According to recent reports from UBS and Morgan Stanley, more than 60% lithium demand will come from electric vehicle battery packs. UBS expects lithium demand to increase sevenfold towards 2030, reaching 36 million EVs sold, demanding close to 2 million tons of lithium carbonate equivalent. Electric vehicle technology is in research and development frontline for major OEMs, investing heavily since 2016, particularly traditional OEMs such as VW, BMW, Hyundai, and Toyota. UBS estimates a 17.4 electric vehicle penetration by 2025, while report consensus is around 15%. If 15 million electric vehicles were sold in 2025, the total power necessary will be around 963 gigawatt-hour, considering each car has around 62 kilowatt-hour capacity. According to cathode chemistry, independently from other chemical compounds, all cathodes use around 11% lithium. Technology is under development, but analysts expect lithium to be the sole element to be present in all future cells. As a conclusion, UBS and Morgan Stanley estimate lithium carbonate equivalent usage in the cathode close to 600 grams per kilowatt hour, and another 100 grams per kilowatt hour may be used in the electrolyte. What is the composition of the battery market today? Affordability, diversity, and energy density of electric vehicles have made markedly increase, supporting the global adoption. Battery costs are a tenth of their price in 2010. Industry battery systems cost overtook previous estimates by $20 per kilowatt hour and should reach $100 per kilowatt hour by 2022, where $20 per kilowatt hour is equivalent to a 1,000 to 1,500 savings per car. Therefore, the total cost gap with conventional cars is expected to be fully closed by 2024. Battery technology is also evolving quickly. Thanks to intensive worldwide research over the past 10 years, new families of solid electrolytes have been discovered and with very high ionic conductivity similar to liquid electrolytes, allowing this particular technology barrier to be overcome. In modern lithium-ion batteries, ions move from one electrode to another across the liquid electrolyte, also called the ionic conductivity. In all solid-state battery, the liquid electrolyte is replaced by a solid compound, which nevertheless allows lithium ions to migrate within it. Solid-state battery represent a paradigm shift in terms of technology and could represent the next frontier by improving safety standards, power capacities, and rapid charging with lithium metal anodes, potentially replacing graphite, which has almost 13 times higher capacity than graphite. BMW, Ford, and Samsung have invested in solid power batteries with the aim to commercialize solid-state lithium-ion batteries by 2025, although solid-state is currently 20 times more expensive than traditional lithium-ion batteries. How do raw materials benefit for this energy transition? Battery metals, including cobalt, manganese, nickel, and phosphorus, among others, are the battery main components. Battery market has evolved exponentially in the last 10 years, and it's expected to continue to increase by 13-fold in the next 10 years, driving step changes in demand for raw materials, especially lithium and graphite, expected to see largest growth in the market size of 8 and 5 times respectively. The rapid rise in raw material demand sees deficit for coming over the next decade. Even if all known projects come to market, prices need to rise to incentivize not only idle capacity to return to ensure supply in 2021, but to encourage exploration investment to medium and long-term demand. This will be a challenge for certain commodities, particularly for lithium, where deficits are projected even when assuming that all current operations go to nameplate capacity and all announced projects come online. What is the outlook for raw materials in the next few years? Commodity prices are rising as market sees a shortfall in production and investment incentivizing new supply. Lithium is a prerequisite for all current and emerging battery technologies. Thus, lithium demand is not at risk from how the cathode technologies evolve. The contrasts with cobalt, which battery markets are trying to shift away from. Market analysts projects long-term CIF for lithium carbonate around $11,800 and for lithium hydroxide around $13,500, roughly 50 and 40% price increase from current levels. The future of natural graphite is subject to conjuncture between two competing materials, synthetic graphite and silicon. Synthetic graphite appears to be the preferred to natural graphite when comparing performance alone in the battery, but it is significantly more expensive. The introduction of silicon into the anode is continuing to gain traction and will provide incremental performance gains to the batteries. Projections see long-term FOB price for graphite flakes at $1,100 per ton, about 51% increase from current price level. Each electric vehicle carries 95 kilos of copper, which compares to the current 20 kilos of copper per internal combustion engine, representing a 75 kilos of incremental demand of copper. Copper demand from electric vehicles is likely to carry less risk than any other commodity because it is critical in transferring power within the electric vehicle. Copper demand is set to explode, but years of underinvestment threaten to leave supply short. Projections see long-term copper at $3 per pound. Nickel is favorably exposed to demand from electric vehicles due to many battery technologies. With the nickel in the cathode, the movement towards using more nickel and less cobalt in this. High-performance batteries require high-grade nickel-fed stocks as opposed to current grade, leading to a large capital commitment in the order of $2 to $5 billion for a 20 to 40,000 tons per annum capacity plant to increase nickel purity. Projections see FOB for nickel in the long term at around $7 per pound. Question today is if we are entering a commodity supercycle and how would this impact? What we are saying is with energy transition, ESG policy and private investment could be the drivers for the next supercycle, but green bottlenecks threaten the clean energy business. There is a crucial role for the states in easing planning rules and helping companies and investors to deal with the risk. The average mining project takes about 16 years to get approval, and this has to be improved in order to be able to meet the current demand. What part does the electric vehicle battery supply chain need to address? Currently, supply chains from Europe and North America focus on global mining and Asian refining of cathode materials. There is a huge pressure to build out European and North American supply chains to reduce costs and create jobs. Many governments and commercial banks are directing funding to the sector. Growth of a battery supply chain allows future sourcing to be optimized, reducing shipping and working capital while reducing political risks across the whole value chain. South America has a key role to play in the energy transition. Total resources identified around the globe are 286 billion tons as of 2020, a 39% increase from resources identified in 2018, meaning lithium is not a rare element, but its economic viability is challenging. Transition to clean energy keeps driving demand for the lightest metals, lithium. The global lithium market is projected to quintuple over the next 35 years. That bodes well for countries in the lithium triangle, Argentina, Bolivia, and Chile, where 60% of the world identified resources. The South American region abundance is partly due to the vast salt flats, where the metal is extracted from brine poles and evaporated and processed, facilitated by the arid and sunny climate. However, we do not necessarily translate into accessible resources or production capacity, which require technology, investment, and a favorable regulatory framework to harness the power of potential resources in the lithium triangle. Argentina and the region have an enormous potential to play a key role in tomorrow's global energy environment. Argentina ranks second in terms of proven reserve, fourth in lithium production and first among US sources of lithium inputs. Most of the mineral deposits are found in the salars in the northwestern provinces of Jujuy, Salta, and Catamarca. There are two large mines currently in operation in Argentina, Salar de Olaroz in the province of Jujuy and Salar del Hombre Muerto in the Catamarca province. Just to finalize, at Orocobre, we have defined the sustainability factor as our key strategic objective, and in the following slide, you can have a quick look at our performance in terms of carbon emissions and water consumed at operations and the way we're working to further reduce them. Our progress sets clear safety, environmental and social objectives and foster a culture of collaboration to drive efficiency, quality and sustainable development at our operations. Our long-term commitment to sustainability and transparent reporting is evident in the recognition from the Australian Council of Superannuation Investors and the inclusion in the Dow Jones Sustainability Australian Index. Thank you.
Hello everybody, thank you for the attention. My name is Oscar Ferreño and my presentation is how to handle intermittency or better variability in renewable energy, the case of Uruguay. Uruguay is a small country in Latin America with a low population density, 3.5 million inhabitants, surface 180,000 kilometers square, no have fossil energy resource, simple and flat topography, economic is totally agricultural. All possible hydroelectric potential fully developed. Annual hydroelectric production is maximal 9,000 gigawatt hour and a median de 7,000 gigawatt hour and a minimal de 3,500 gigawatt hour. Annual electricity demand today is 11,000 gigawatt hour with a growth rate close to 2% and a maximum power demand peak of 2,000 megawatts. Argentina international connection is the 2,000 megawatts. There is a Brazil international connection with 570 megawatts. Argentina has abundant fossil resources. Uruguay fed the domestic electricity demand with the generation of hydroelectric plants, complementing and supporting them with thermal energy imported from Argentina. Uruguay electricity system was very vulnerable to the economic and energy problems of Argentina. Different alternatives for electricity generation began to be analyzed. Nuclear power plant, regasification plant, and renewable energy. Also, wind power and photovoltaic was viewed as possible alternatives. They were seen as marginal solution. It is true that the first decade of this century, no electricity market showed shares of wind or solar energy greater than 10%. They say, let's not pretend that the wrong conventional renewable energy solves the energy problem, but we do want them to collaborate to do so. This route was based on the so-called intermittency of wind and solar photovoltaic. Uruguay experience. The Uruguay experience showed that these firsts were unfounded. In fact, this electrical system has functioned as a laboratory where the viability of these technologies could be verified. Today, wind and photovoltaic have totally displaced fossil thermal generation, leaving this only for a backup that can be considered as emergency. There are several reasons for this behavior. One, solar photovoltaic and wind power are not really intermittent, but are persistent variables. Two, there is a natural complementarity between the wind resource and the solar resource. Three, there is also a natural complementarity between hydroelectric production from reservoir plants that allows some management of their production and wind and solar plants that are not manageable. The hydraulic phenomena are of low frequency, with the variation of the wind and sun are the high frequencies. Reservoir hydraulic plant has reliability in short and medium term, but they have not in annual terms, while photovoltaic and wind power plants are predictable in annual terms. Four, the reservoir acts as a true energy storage battery. The variable renewable energy displaces the hydroelectric plants to the reservoir and these accumulate their natural flow. Uruguay has a great interconnection capacity with Argentina. This increases the region where renewables energy has influence and causes attenuation of the variations. It's possible to keep this in the future. The reservoirs have contributed to the integration of the variable energy. This composition of the current generation park will only be enough to supply the vegetative growth of demand for the next 8 to 10 years. If we want to continue supplying electricity demand with not conventional renewable energy, we must resort to a complementary storage to that provided by hydraulic plants. It is necessary to determine what characteristics of this storage should have in terms of the reservoir capacity over time. Photovoltaic plants have a clear frequency of daily variation, but it also has a seasonal variation. A photovoltaic park wind tracker has a capacity factor of 24% in Uruguay, but this varies between 13% for the June-July 2 months period to a 35% for the December-January 2 months period. It is more difficult to identify variations in wind capacity factor. The following graphs show the capacity factor of the best wind farm in Uruguay, totaling 1,190 for 1 day, for 10 days, for 30 days, and for 60 days. This is the capacity factor 1 day, May to May, for 1 day. This is for 10 days. Factor de capacidad for 10 days. This is for 30 days. And this is for 60 days. In the graph of 30 and 60 days, the difference in the capacity factor of the wind power between winter and summer can be clearly seen, partial due to the higher density of the air in winter and partial to the higher wind speed. That is complementary to solar photovoltaic production. On the other hand, the variations of the wind power capacity factor in 10 days are of the order of 45% in winter and 20% in summer. While for 30 and 60, these differences are less than 10% in both winter and summer. This leads to suppose that the ideal is to combine the solar source with the wind source and with a storage capacity of the order of 30 days to 60 days. Let's now see in the following figure which are the storage technologies that the best adapt to these characteristics. Here is different storage technologies. Here we have a flywheel is for 1 hour, 100 kilowatt hour. Then is the battery. Then is the compressor eye storage. This is hydraulic pump station. This is hydrogen, and this is natural gas synthetic. For the characteristics of Uruguay, with an annual electricity market of 11 terawatt-hour and a need for storage around a month, the only technology that are adapted at the storage is using pure hydrogen or using synthetic natural gas, which is obtained through hydrogen. This is very interesting since the only way to decarbonize the energy matrix is to gradually replace the energy from fossil fuel with hydrogen produced by non-conventional renewable energy. The Uruguayan fossil fuel market is between 4 and 5 times the electricity market. If the market begins to be replaced by green hydrogen obtained from non-conventional renewables energy, the problem of non-conventional renewables energy variability will be gradually resolved, since this hydrogen it will also serve as storage. Two questions might arise. Is there enough potential in Uruguay? It is economical competitive. For wind power in Uruguay, there is a rate of 1 megawatt each 30 hectares. If we consider that there are 40 million hectares dedicated to agricultural tax, we see that the potential is several times than necessary. Regarding economic viability, today the production of green hydrogen with dedicated wind and solar energy will be around $6 per kilogram. The caloric value of the hydrogen is 3 times higher than of the fossil fuel, and the efficiency of the use of the hydrogen is electromechanical activity can be up to twice the use of fossil fuel. That brings the cost of the green hydrogen close to the cost of fossil. Also, it's not yet competitive. However, the expected technological development will bring in closer at the same point will we have to monetize the environmental impact of continuing to emit greenhouse gases. Thank you very much.
Good morning to Martin in the United States and Oscar in Uruguay. Good afternoon to Ulrich in Germany and Eloy in Spain. And good evening to Watsuo and Masakatsu in Japan. We have 20 minutes allocated for our panel discussion. So I would appreciate if you could keep your interventions brief. The first question goes to Ulrich. Energy models often pose challenges regarding metrics assumptions that can lead to results that not always are comparable. You described an approach that allows to forecast and manage greenhouse gas emissions. So the question would be, is there a reasonable consensus on the metrics applicable to standard emissions related to the leading energy technologies, or are there different criteria?
Yeah, thank you very much, Roberto, for this question. The simple answer is no. Of course, there's not one single method or a consensus on the choice of methods, but of course, the choice of method depends very much on the question you'd like to answer. So in a very simple case, you would choose the matrix of emission factors based on the annual average. So this is the most simple version, and this number is available for most international countries. If you want to be more precise, you have to go into a higher resolution of electricity generation and emission factors. So typically 1 hour or 15 minutes, or if you want to be very exact, even 1 second, depending on the intermittency of PV and wind emission. And if we do so how we're working with higher resolution, the next question arises whether we use the mix of electricity or we choose a marginal or incremental method. So deciding whether a new application makes it necessary to start a new power plant, for instance. So this would be an extreme case, but quite realistic. And the third option is regarding flexibility. So applications which react flexible on the availability of renewable electricity. And this is, of course, is the most interesting and the most promising version, but also, of course, going along with high computation times and more complex systems. And of course, it would make no sense to have very complex models with very long computation times where the result is available later than the target year, for instance, in the extreme case. Yes, still a lot of work to do in modeling and also in finding methods with a consensus between the different nations, right?
Thank you, Ulrich. The second question goes jointly to Atsuo Yamada and Martín Pérez de Solay. Your presentations allowed to highlight the dynamic development of batteries and of those minerals required to manufacture them. If you had to choose just one high-level message for key decision makers regarding the challenges ahead, Atsuo, how would you draw their attention on cost reduction? And Martín, where would you place the emphasis on the level and sequencing of investments required to expand mineral supplies? Atsuo, the floor is yours.
Actually, that is not my specialty, but I've tried my best to answer that question. For the cost reduction, it depends on the several factors. It's on the market becoming huge. The mass production will become large, and that will naturally reduce the cost. But the high demand for the materials themselves will naturally increase the cost themselves. So it's a balancing issue. So I have no idea for that. So in my presentation, that it's the best way to shift to the abundant element itself. So the sodium and the iron and water, that will be the ultimate one. So the issue the human beings should explore is that kind of direction. And I am dreaming for that kind of direction. So, but for the short term, for cobalt and lithium, that will be depend on the market force. So I don't have any idea to answer. Is
Thank
it all
you.
right?
That's very clear. Thank you. Martín, please.
If I pick it up from Matsuo's point, I think number one point is, given the time it takes to bring upstream projects, mineral projects onto production, we have to be very careful how to choose and how we sequence the investment. From Matsuo's point, it is very important to understand the market and which are the molecules that the market will require and tailor our offer to the market needs. Obviously, we have to focus today in the sustainable sources for producing lithium and battery materials. Nobody wants to buy an electric vehicle that is made from non-sustainable sources. So focusing on the sustainability is the key element. When you put those things together and you try to sequence investment, what that will tell you is that we'll have to focus on investing in those resources that can deliver product into the market very quickly, highly sustainable, and at a very in a very cost competitive format. The other thing to take into consideration is that we think we all need to continue to invest a lot of money in technology. Technologies will evolve over time, and we have to be able to supply a market that will grow as much as these markets. The electrification of the world will require lots of new minerals to be developed. And as you see in the next 5 years, the requirement is going to be, we're talking about 5 times for all different materials and different growing curves and else. So that's how we would sequence the investment.
Thank you, Martin. The next question is also a joint one for Masakatsu and Eloy, who dealt with hydrogen. Your presentations provided a comprehensive view on the development status and prospects of hydrogen in Japan and Europe. I would ask Masakatsu to briefly comment on the hydrogen strategies of China and Australia, and eventually any other country in Asia Pacific that you consider relevant, and Eloy later to give us a snapshot of the US policy. Masakatsu first.
Okay, thank you. So talking about the Australia first, the Australia has quite a different perspective regarding the hydrogen against Japan, because Australia is going to be an exporter of the hydrogen as a fuel, while the Japan is definitely the importer. So that contrast is quite significant. And talking about China, it's quite complicated because the China has a lot of land area, but not all of them are good for the renewables, but still they have a good potential for the solar and wind in some regions. So the China has quite a complicated situation about the hydrogen strategy. I mean, how they can afford the hydrogen domestically, or in some case, whether or not they have to import the hydrogen from other countries like Australia. So that should be probably the still a target of the discussion.
Thank you. Eloy, on the US, please.
Well, thank you very much. In relation to the United States, I believe that the document that could be more relevant is a document of the Department of Energy, that is the Hydrogen Program Plan. And my understanding is that really there is a clear difference with the approach of the European Union and in Europe, in the sense that, for one hand, I believe that the objectives are not so ambitious, because if today the United States consume around 10 million tons of hydrogen per year, really the estimations are that could be in the level of 22 or 40 million tons per year in the year 2050. So it is multiplied by 2 or 4. And secondly, and perhaps also important, is that the renewable hydrogen is, of course, a possibility, but they, looking at the document, they also understand that gas, particularly I understand shale gas, that is very competitive, could be a fuel that could be continued using in a efficient way. On the other hand, the consideration of carbon capture and storage that the United States has really great experience, because the oil and gas industry can help also to that. Another thing is that although in Europe the emphasis is almost exclusively in renewable hydrogen in general, really the nuclear generation could really help to produce a very competitive hydrogen, because of the continuity of the number of operating hours that are more stable and less intermittent than renewables. So nuclear is also considered in this respect, and finally also coal. So I should say that it is, let's say, more open. And finally, in terms of consumption, final uses, I mean, really the great emphasis is in transportation and in the synthetic fuels production.
Thank you, Eloy. The next question is for Oscar. who talked, as you remember, about wind solar. You stressed the importance of quote unquote variability management in solar and wind power generation. Could you elaborate on the difference between this and the more extended concept of intermittency?
Okay, thank you, Roberto. Wind power generation, and photovoltaic solar generation are often mentioned as intermittent. This will be true only if they were focused in one spot, in one point. The reality is that the wind and clouds are moving and attenuating the variations in the production. The greater the dispersion of the solar and photovoltaic parks, the lower the power variation. That is why I mentioned that they are not intermittent but persistent variables, because it tends to be constant. If for that is very important in agri-region, we have international connections. Also, to mitigate the variability, it's necessary storage capacity in Uruguay or in the region for 40 to 60 days. This is only possible with hydrogen or ammonia in the future.
Thank you, Oscar. We have another question from Yves Van Berger. Sorry, I put off my camera for a second. Directed to Masakatsu Sugiyama. And the question is, what about nuclear in Japan, considering your presentation?
Okay, so the nuclear is, of course, in principle, a way for decarbonization of the energy system. But the people's acceptance about the nuclear is quite subtle in our country because of that disaster in Fukushima, which was 10 years ago. So now we have a competition for the new possible prime minister, and we have a very deep discussion about how we can use or abandon the nuclear power plants. And the most severe issue is that the nuclear fuel cycle is not established in Japan. And also we have not so large perspective for doing that in the coming years. So that means we still have to struggle with the issue of the waste of the nuclear in Japan if we want to continue the use of the nuclear or introduce the new nuclear power plants like SMRs. So that is actually a quite high barrier, probably compared to other countries for the Japanese usage of the nuclear. So my simplest answer is that it should be still very, very limited capacity, I think.
Thank you. We have another question from Maria Soledad Calcaño. In principle, I would suggest it is directed to Masakatsu and Eloy, and I would ask you both to be relatively brief because we have other questions. Is certified low carbon hydrogen, known as blue hydrogen, taking into account indirect emissions generated by an increase of production? Okay. Who wants to go first? Masakatsu?
Okay, right. So the simplest answer in my conception is that there is no worldwide accepted way of certifying the carbon CO2 footprint in hydrogen, and that is still under discussion. And it's maybe still long for the worldwide to establish that scheme of the carbon traceability for the hydrogen. So the way of incorporating such kind of indirect emission of CO2 in its production process, as well as the transportation and other relevant process, is still at the target of the discussion, I think.
Perhaps I can say something more. One matter related to this is the certification of renewable hydrogen. In Spain, in the instruments that are provided or planned in the roadmap, it is expected and planned to specify a clear and standard certification for hydrogen, renewable hydrogen. In relation to the blue hydrogen, my understanding is that there are international and companies, auditing companies, that certify the emissions. And my understanding is that depending on the scope that can be considered scope 1 or scope 2 in relation to the emissions of CO2, my view or my impression is that these indirect emissions of fossil fuels could be considered, if particularly you consider scope 2 or scope 3.
Yes, thank you both. We have another question from Yves Bamberger, directed this time to Eloy, and it is, how many tons of CO2 were produced by the combustion biofuels in Spain?
The precise number, I am sorry, I don't have it at the moment, but some other data could be of some reference. The production of biofuels in terms of millions of tons of oil equivalent in Spain in the last years has been around 2.2 million tons of oil equivalent. And on the other hand, it is some data point out that the use of biofuels is reducing around 60% of the CO2 emissions of conventional fuels like gasoline or kerosene. So this is something that I can tell, and last data that could be of some help perhaps is that the emissions of bioethanol, biodiesel in terms of grams of CO2 per kilometer is around 140. But the exact data, I'm sorry, I don't have here at this moment, and I will look it and provide it to you and to Yves at a later moment. Thank you.
Thank you. That is very kind. We have another question from Chai George Okoye from China, which I will address to Ulrich, and says, how many tons of CO2, since the purpose of promoting the use of electric vehicles is to mitigate greenhouse gas emissions, which are responsible for climate change, how can developing countries still struggling with constant electricity be able to use electric cars which would need to be charged from time to time?
Yeah, thank you very much for that question, which indeed is very relevant, because politicians in Germany for a long time sticked to the goal to reduce electric consumption, and it took some time before they understood that increasing electricity consumption helps. And meanwhile, last year we have a new legislative which puts new goals, including an increase of electricity consumption in Germany. And just to name two numbers, the electrical consumption in Germany actually is about 600 terawatt hours, and 1 million of extra electric vehicle consume 2 terawatt hours. So quite a small number in comparison to the total consumption for the moment being. And if we have the goal to achieve about 80% of electricity generation by renewable energies, it is for sure that we need more electric consumption in traffic, in industry, in household, including electric heating. So these are goals which were quite forbidden. Yeah? The discussion about this was a taboo in Germany for many years, but this has changed, fortunately.
Thank you, Ulrich. We are now coming to a close, so I would like to thank you all for your excellent presentations and for this lively and enriching discussion. This session has provided insights on the opportunities and challenges of renewables, the balance between aspirations and actual achievements will have the final say. I would also like to thank the audience for joining us and sending us their questions. We will now see 2 WEC startup presentations, then go to a break, and please stay tuned afterwards for session 4 on oil and gas. Thank you very much for your attention.
Thank you.
Please join me in welcoming WEC Startup Energy Transition Awards finalists set 2021.
Hello, my name is Hamad Beheshti, the co-founder CEO of Boreal Light, and it's a pleasure to be with you in this conference today. I'm presenting our work in Africa, particularly in East Africa, on decentralized solar water desalination solutions for off-grid communities. Since the presentation is a recorded one, if there is any question, comments, follow-ups, there might be interest, whatever, I'm sure the conference managers, they would arrange for sharing the contact addresses of those who are presenting. And in the meantime, feel free checking our website, windshare.de. And should there still be any questions, clarifications needed, feel free contacting me. I share my screen now, and then we can go through the journey we've done in East Africa, transforming the unprivileged rural communities into productive, sustainable communities, being sustainable, starting from water, continues into every aspect of their lives. So join our journey, and let me just share my screen. So here we have Water Kiosk, the project created by Boreal Light for rural communities around the world. At Water Kiosk project, we looked at the problem of rural communities in two main aspects, and then we widen our aspects of making fundamental change in the economy of rural communities. The first problem we started tackling is the quality of drinking water in remote part of the planet. And imagine a market like East Africa, 1,000 liters of this quality water from this canister and bucket, which is non-reliable, is unsafe, bacteria, viruses, different minerals contamination, costs $10. And in dry season, that even goes to something like $60. It's insane for such people with the lowest income in the world. And then it's not just drinking water. The problem is even greater. Farming is in trouble now in the world. Salt intrusion is a common problem and common challenge for many rural communities now. This is a direct impact of climate change. Normal boreholes that for generations they were supplying water for farming, now they are turning saline. Look at the picture. The part that was irrigated, you see salt accumulation. The part that was not irrigated, you see vegetations there. This is a huge dilemma for communities that they are built on the practice of farming. Hygiene drinking water in practice and having it for every person in this planet. In the market that we are presenting today, it costs a lot. Imagine, this is the water that we call it hygiene drinking water. 20 liters of this water costs $4 in East Africa. That means 1,000 liters of it costs $200. This is extremely high for villagers that maximum they may earn something like $80 per month. So imagine then for 1,000 liters of such water, and just for drinking water, they pay $200. That's for sure insane. The solution we brought to tackle this challenge is a solar water desalination system with three main characteristics. One, running fully on solar energy, no need of battery, no need of pressure storage, no need of diesel, no need of anything, just solar panels and the machine. The second characteristics, which is very vital for us, is the simplicity of the systems. Systems are designed by nature to be simple so the locals can operate, maintain, and taking care of it. And then the result of this too is the affordability of the machines. The machines, this is our production hall in Berlin. Actually, this picture is from 2 years ago, so these machines are already delivering water to thousands of people. You see the sense of simplicity there. You see the space there that is making the work much easier for locals to do the maintenance. And a normal plumber in a village with these two tools can do over 80% of the maintenance. A wrench and screwdriver, no sophisticated machineries, no sophisticated techniques is needed. Just a wrench and screwdriver, you are done with over 80% of the maintenance. This makes the water production so cheap. So producing 1,000 liters of hygiene drinking water from super saline water source would not cost by this machine anything more than $50. So we started thinking, instead of just selling the machine, that we are selling the machine, let's sell water. These columns that you see here on the left are the bottles that I myself purchased when I stay in East Africa. So you see the average cost of the left columns is $4, means 20 liter. The average price is $4. We started selling water in urban communities for $1 per 20 liter, in village communities for 10 cents for 20 liter. You see 1/4 of the average market price and 1/40th. And it's not just the technology. It's tackling also the beyond technology aspect, that is talking about social business and circular economy. And in practice, social business and circular economy, when it comes to our project, means we bring the machine at the heart of a village. We get the raw water from, you see from the left side, we are getting the raw water. Then we bring it to the machine. From right side, we are delivering drinking water. Then you see we are delivering irrigation water. And then the wastewater of the machine goes for spirulina farming, goes for fish farming, because we are not using chemicals, so easily we can grow fish. And lastly, we are using the wastewater for sanitation. Then you can imagine how much of impact it brings, this setup, to the rural communities. These are some of our kiosks that you can see the way that they look like. On the top right one is a direct ocean water. Bottom right one, you see the solar panels on top of the kiosk. Sometimes solar panels are on top of the kiosk, sometimes in the nearest rooftop. Depends where the project is and what are the specification of the projects. But these are all farms, from the vertical farms to drip lines. These are all fish farms. So simple. You see, simplicity is important, and at the meantime bringing the high quality protein as a daily food for people. These are operators. Look at their face, how young they are. The youngest of their the youngest people in the village being able to run the machine, operate the machine, and creating a carrier. Here is one of the layout of one of our projects. You see the ocean, borehole, solar panels, and the machine, and the dense community. Here is different. Here is a village community that where you see the solar panels, the machine, fish farm, vertical farm, sanitation, all distributed and making a huge impact to that community. It's not just the issue of simplicity. When you are not watching the machine and helping them, helping the operators, still there are challenges there. We are reading on a 24/7 basis 36 vital elements of the machine from Berlin. The same screen on the left we are seeing in Berlin, the operator sees on the machine. And if anything happen, we can go one-on-one, just helping the operator managing the things in the machine and then maintain it. So they are not left alone there. The other big impacts of water kiosk project is also the carbon credit, the CO2 offset. So every water kiosk on average is saving 500 tons of CO2 per year. And our records is now all over the world, so mainly in Africa and also in East Asia, in the Philippines, Indonesia, and we would love to be very soon in Central South America. Actually, we just started work in Mexico and we are expanding then into the region. Thank you so much for your time. Appreciate it. And then if there is any question, comments, please let me know. Thanks.
Hello everyone, thank you for giving me the opportunity of being here speaking about my company. I'm Sebastián García Marra, co-founder of LES Industries. So let me do a quick introduction. LES was established in 2014. We've been developing industrial IoT solutions for the last several years. We are based in Argentina, Australia, and Germany, and we have deployed more than 20 projects in several countries around the globe. At LES, we have a distributed team. I'm going to briefly introduce it in just a minute, but first let me introduce the founder team. So this is the founder team: Lucas Chiesa, Andrei Vasnov, Sebastián Ceroni, and me. We've been working together for a long while, even in projects before LES, and we are always contributing from different backgrounds and perspectives. As I mentioned before, we are currently a distributed team. We have 11 people across the world, with people based in Spain, Germany, Argentina, Australia, and we are actually very proud of our team. So that was a quick overview about the company. Now I'm going to tell you about the main solution we're deploying, but firstly I have to talk about the problem we are tackling. Power lines are a non-digital asset vastly distributed, which turns out to be a problem when it comes to how to monitor those assets. Then let's see. The grid's needs are changing. The climate change as well as the power demand are affecting the grid. The climate change is an issue because, as we all have witnessed, the weather is becoming more extreme. In recent years, we have snowstorms, wildfire, among other phenomena affecting the lines. But there is also an increasing power demand that is going to be huge in the coming years due to the increased number of electric vehicles. For addressing these issues, there are two main actions to take: increment the power capacity and perform smarter monitoring of the line status and condition. At least we are tackling the second part of this problem. We have developed a solution that solves the issue of knowing when and where a condition is taking place in the line. By hanging devices straight in the cable, we are able to measure conditions such as that the tower has fallen, a cable has been cut for whatever reason, that the strong wind condition is taking place, and so on. We can report the incident in real time so people in charge of taking action will know immediately. But other than that, we are stepping in monitoring vibration patterns, which leads us to have insight on the health of the line in terms of corrosion, aging, broken strand, ice deposited in the line. So summarizing, we can also offer a powerful predictive maintenance tool. There is plenty of customer benefit, but these are just one of those. 90% save cost for fault detection process, up to 1 span accuracy. Dramatically reduce failure identification time from 4 hours to 2 minutes, and hotline installation. We also have some milestones as of today, such as 400 devices sold, a patent pending, and a certification regarding corona effect. Our most important client so far is Transelect, who's been working with us for the last 5 years. And we recently closed a deal with a new partner for distributing the product in 30 countries. Thank you for listening to me. Bye.